The purpose of this slide deck is to introduce sums. This deck is split into two videos. In the first video, we introduce summation notation. This allows us to present the Gauss summation trick, which is often used when counting the number of pairwise interactions in a population of components. In addition to describing the adding of values of a finite collection of numbers, summation notation can also be used to talk about adding arbitrarily many numbers together. In the second video, we show two examples. The infinite geometric series is a common example of a convergent series. The infinite harmonic series, on the other hand, is commonly used as an example of a divergent series. In this video, we begin with notation. The uppercase Greek letter sigma stands for sum, and this notation is read as S equals the sum from k equals k0 to kf of a sub k. The letter k is an index. Each individual integer value that k can take is associated with a particular value of ak. This cartoon illustrates both positive and negative AKs. The starting value of k, meaning k0, corresponds to a sub k0, and the final value of k, meaning kf, corresponds to a sub kf. Values of ak for k less than k0 or greater than kf are excluded from the sum. Summation means to add the AKs as illustrated by stacking these bars vertically. The net value of the AKs is S. We have just presented how summation notation describes adding together the values of a finite collection of numbers. To practice working with this notation, we will describe the Gauss summation trick, which is used to count the number of pairwise interactions in a population of components. In this example, S refers to the sum from k equals 1 to n of k. In other words, 1 plus 2 plus 3 and so forth up to and including n. S is equal to half times 2 copies of itself, which is again 1 plus 2 plus 3 and so forth up to n. We change nothing by adding the terms up in reverse, meaning n plus terms decreasing by steps of 1 all the way down to 3 plus 2 plus 1. Notated compactly, this is the sum from k equals 1 to n of n minus k plus 1. Do you agree? Because the indices on both sums are now aligned, we can add their contents, that's the k and the n minus k plus 1, inside a single sum. You might want to revisit this point and sketch an inescapably persuasive figure, starting with the graphically illustrated definition of a sum on slide 2. Cancel the plus and minus k to obtain 1/2 times the sum from k equals 1 to n of n plus 1. Adding the constant number n plus 1 over and over again n times gives n multiplied against n plus 1, and dividing by 2 gives n times n plus 1 over 2. Adding 1 plus 2 plus 3 up through n gives n times n plus 1 over 2. The interested viewer may wish to search the internet to study how this sum represents the number of pairwise interactions between n plus 1 interacting individuals. We have just practiced working with summation notation to study adding together the values of finite collections of numbers. In the next video, we will illustrate how summation notation can also be used to talk about adding, without end, more and more numbers to a running total.